So I just talked about correlation as a description of association between two continuous variables. We can also treat it as a hypothesis. In that case, we're hypothesizing that there is a significant association between the two variables, which means the null hypothesis is that there's no correlation between the two variables. So basically, we're going to be computing a correlation statistic and comparing that to 0. So what I did to try and give you a sense of how this works is I used the statistical program R to compute 12,000 correlation coefficients. And those correlation coefficients are a histogram of those correlation coefficients is plotted here. Each of these observations describes the association between two samples of 10 observations from the standard normal distribution. So I picked 10 numbers with a mean of 0, a standard deviation of 1, and I associated them with 10 other observations with a mean of 0 and a standard deviation of 1. They found the correlation between those. So you can see, so in all of these simulations, the true correlation should be 0, right? There was no actual underlying relationship between the two variables. Any association just due to random chance. I happen to pick the big ones in the x variable at the same time as the big ones in the y variable, and the little ones, vice versa. So you can see that, as we expect, most of the correlations are near 0. But when you look at thousands of them, you get, just by chance, some correlations come out really strong. Either they're almost in a perfect line going up, or almost a perfect line going down. So this is what we're talking when we're talking about even when the null hypothesis is true, that there is no relationship between the two variables, we will sometimes see a high correlation or a low correlation. So we need to compute a test statistic to see how much we believe that our particular correlation that we're observing is not just random chance. And so we do that with a single sample t-test. So here's that same correlation distribution of correlations that I showed before. So most of them are around 0. Some of them are low, some of them are high. But here, what I'm plotting is the standard error of the correlation coefficient for a sample size of 10. So what that's saying is that the standard error is pretty low when your correlation coefficient is -1, and it's pretty high when your correlation coefficient is 0. It goes back down here. So we expect the error to be larger when we're close to 0 and smaller when we're at the extremes. And so then we divide the frequency of each of these by the standard error, or we divide the observed correlation by the standard error here, and we get these this t distribution. So the black, again, is the observed values from this thing divided by the standard error, and the red is the theoretical t distribution with 9 degrees of freedom. You can see they match super well. So then we can do a single sample t-test. So again, we only care about a positive. Oh, that's funny. They came in the wrong order. So if the only kind of correlation you care about is a positive correlation, then it's a one-tailed test. If the only kind of correlation you care about is a negative correlation, it's a two-tailed test. If you care about both positive and negative correlations, positive one-tailed, negative one-tailed, two-tailed. Goodness, I need more coffee today. So as always, in this class, we'll use the magical value of 0.05, the alpha value of 0.05, to compare our p's to. So if our p value is less than 0.05, it means the two variables are associated. But that doesn't tell us about the strength of the relationship. If you have a really big sample size, you can get a significant p-value with a really small correlation. So you want to report the actual magnitude of your correlation in addition to your p-value. So if, for example, you have two continuous variables, foo and bar, and the correlation between them was 0.628 and the sample size was 21, then you would write out there was a significant positive correlation between foo and bar, little r, subscript 19, equals 0.628, p equals 0.002. So this little r means you did a correlation. This 19 is the degrees of freedom, And you lose 2 degrees of freedom from the sample size because you're calculating a mean for each of your variables. And then this 0.628 is the actual correlation we computed. And then the p is something you looked up from the t-distribution. So you would change the names of the variables, the degrees of freedom based on your sample size. You change the correlation based on what you actually got in your calculations, and you change the p-value if you're using this as your template to report. That is it for correlation as a hypothesis.